Hello everyone, let's go ahead and take a look at Rolle's theorem and the mean value theorem, both of which are an application of differentiation. Let's start off with Rolle's theorem. Rolle's theorem says let f be continuous on the closed interval ab and differentiable on the open interval ab. It says that if f of a is equal to f of b, then there exists a c on the open interval ab such that f prime of c is equal to 0. So again, let's go through the same process of visualizing what exactly this is stating. So here we have a graph. Here's our x-axis. Notice that we have the function continuous on the closed interval ab and differentiable on the open interval ab. And notice that in this particular case here, f of a is equal to f of b. So here's f of a and here's f of b, both of which are exactly the same range value. Now, if I'm going to have a function that is going to be differentiable and continuous, then of course I'm just going to go ahead and draw any function that I want. And then I'm going to go ahead and say that if those conditions are true, then there has to be a c between a and b such that f prime of c is equal to 0. So in other words, there has to be certain stationary points on the function between a and b. So if I go ahead and take a look at what I've drawn here, here's my function. I have a stationary point here, here, and here, which means then if I go ahead and draw this dotted line down to the x-axis, then I would actually have 3 points which would actually satisfy this result. And I call those points c sub 1, c sub 2, c sub 3. Now again, we're talking about an existence theorem, so you have to guarantee that there is at least one, but there of course could be more. Now let's take a look at a particular example here. It says prove that f prime of x is equal to 0 on the closed interval negative 2 to 2 if f of x is equal to x to the fourth minus 2x squared. Now I'm going to go ahead and directly take the derivative here because we're going to have to use that. We have f prime of x is going to be equal to 4x to the third minus 4x. Now we need to go ahead and check the conditions. Again, remember that for all of these theorems, if your conditions are true, then the result will necessarily be true as well. So the conditions are that the function itself is continuous on the closed interval from negative 2 to 2. And sure enough, if we go ahead and take a look at our original equation here, there are no points of discontinuity, and therefore it is continuous. Is it differentiable on the open interval from negative 2 to 2? And again, if we take a look at the derivative shows no points of discontinuity on the open interval from negative 2 to 2, so we are okay as well. Now the last part is we need to go ahead and check this condition here, which says that f of a is equal to f of b. Well, if I go ahead and take a look at f of negative 2, which is this, and f of 2, which is equal to this, clearly we can see that f of a is indeed going to be equal to f of b, and so therefore this condition is also true. Therefore, we know that there has to be a c on the open interval from negative 2 to 2, such that f prime of c is equal to 0. Now, of course, Rolle's theorem stops there, but oftentimes we want to actually go ahead and find out what those c values are. So if I go ahead and set f prime of c equal to 0, so here's my initial statement here, follow through with what f prime of x is, and substitute c in for the x, and then use our usual techniques to go ahead and solve that, and in this case we're using factorizing, as well as a zero product property, to come up with 3 possible c values, 0, plus or minus 1, all of which are on the open interval from negative 2 to 2. So we know that we found the c values that are existing based upon the validity of Rolle's theorem applied to this function on that particular closed interval. Okay, so what we want to do next is we also want to go ahead and take a look at the mean value theorem, which is one of the most interesting theorems that we have in this particular section here. And it says if f is continuous on the closed interval ab and differentiable on the open interval ab, then there exists a c that is on the open interval ab such that f prime of c is equal to f of b minus f of a divided by b minus a. Now the one thing that you want to go ahead and take a look at with regards to the differences and the similarities between these two theorems is that the initial condition is both the same. If f is continuous on the closed interval AB and differentiable on the open interval AB. After that, there's a little bit of a change. This one over here, we need this additional condition to show what we want to be true. In this particular situation here, so long as you have those first two original conditions true, then you can immediately jump and say that you have the existence of a point on the function's derivative on the function such that the instantaneous rate of change at x is equal to c is equal to the average rate of change of the function on the closed interval from a to b. So let's go ahead and again take a look at what's happening here for this particular function. If I know that f is continuous on AB, so here's A, here's B, and it is differentiable on the open interval AB, then there exists a C such that the instantaneous rate of change at x equals C is equal to the average rate of change of f of x on the closed interval A to B. Now the way that I like to do that, if I go ahead and say that this is A, here's f of A, here's B, here's f of B, and what I'm going to do is I'm going to take a look at the average rate of change first. So, if I go ahead and right there, that would be my average rate of change. Now, if I go ahead and maintain this gradient and I just move it along the curve, then of course, what I'm going to find is that there's actually going to be a point on the curve such that the instantaneous rate of change is equal to the average rate of change. And that's where that is. So if I draw a dotted line on here, then that's the particular value C that we're looking for. So, let's take a look at a particular example, and let's go ahead and apply the mean value theorem to f of x is equal to the square root of x minus 2 on the closed interval from 3 to 6. Now, what I've done here is I've gone ahead and actually drawn that particular function here. So this is the 3, this is the 6, f of a is actually going to be equal to 1, and f of b is actually going to be equal to 2. Okay, now before we actually go ahead and take a look at the mean value theorem, being that we have a radical function, let's go ahead and make sure that the domain is well stated. So we know that x minus 2 has to be greater than or equal to 0, therefore x has to be greater than 2. And let's also go ahead and find out what the f prime is. And we know that that's going to be 1/2 x minus 2 raised to the negative 1/2 power. Now, taking a look at this, the domain, of course, is going to be that x cannot be equal to 2. Let's go ahead and state it that way as well. Is that x cannot be equal to negative 2. Okay, so let's go ahead and start off here. It says, what are the conditions that need to be satisfied? Well, is this function continuous on the closed interval from 3 to 6? Well, if we go ahead and take a look at our original function, we know that the domain of that function is x is going to be greater than or equal to 2, and therefore, being that our closed interval is from 3 to 6, we know we're okay. Is it differentiable on 3 to 6? Well, if we check the first derivative, the first derivative, of course, has a point of discontinuity at x is equal to negative 2. X is equal to 2. And therefore, we know that we're okay because we're only concerned about the open interval from 3 to 6. Now, being that we have these two conditions satisfied, we know that there exists a C on the open interval 3 to 6, such that our instantaneous rate of change at C is going to be equal to the average rate of change on the interval, closed interval from 3 to 6. So what I'm doing is I'm applying this initial statement here, because our conditions are true, and then I just go ahead and follow through. So f prime of C is going to be 1/2 C minus 2 raised to the negative 1/2 power is equal to f of 6 minus f of 3 divided by 6 minus 3, which is going to be 1/3. Now, of course, we wanted to go ahead and go further than this, as we want to find out what those values of C are. So if we go ahead and solve for C, again, basically what we need to do is we need to just go ahead and say that C minus 2 to the negative 1/2 is equal to 2/3. Raise each of the left hand and the right hand side to the negative 2 power. And so C is going to be equal after adding 2, c to both sides, c is going to be equal to 2 plus 9/4, which is 4 1/4. And notice the most important thing that we want to check is that that c value is actually on the open interval from 3 to 6, and sure enough, it is. Right there. So, let's go ahead and wrap up things. The Rolle's theorem and the mean value theorem are both applications of differentiation. Again, so long as we can go ahead and make sure that our conditions are true, then we can go ahead and state that the result is true as well. And we need to go one step further and actually be able to find out what that value of c is. And so, again, the same thing for the mean value theorem, except for conceptually, please remember that for the mean value theorem, the instantaneous rate of change of the function at x is equal to c is going to be equal to the average rate of change of the function over the entire closed interval ab. Okay, so we'll take a look at more examples and take some questions, as well as look at the proof of this. This is a very, very nice theorem because it has a very nice proof as well. And we'll go ahead and see some applications of the mean value theorem as well. So we'll take some of those questions the next time that we meet in class. See you there. Bye-bye.